This is the first video for Chapter 2 in Optics out of Hecht. So in this video we're going to focus on waves and the wave equation. First we'll describe the wave equation after a little introduction, then review how we can find speed, frequency, wavelength, and other variables from the harmonic function of a wave. Look at how to apply the wave equation to determine if a function is a traveling wave, and more examples. So let's get right into it. Light is what we're talking about. The underlying principles of optics are things that happen to light, are the properties of light. And light, which is an electromagnetic wave or electromagnetic radiation, has both wave and particle properties. Light is the only thing that does this. We'll say this frequently, the only thing that exists that's massless that exists with wave and particle properties. So it's very unique. So we're going to start by describing light as a wave, and I want to give you initially an image that you're pretty familiar with. And this is an image of the electromagnetic spectrum. You've probably seen it in many classes. This one comes from NASA. And what it's showing you is from the left to the right is a range of different wavelengths, from long wavelengths to very short wavelengths. The reason it's arranged that way is because we go from low energy to high energy, and it just makes sense to us as physicists to arrange things in order of increasing energy. Something that I'll ask you now is, what is light? Is light beyond this little part here that's visible light? What counts as light? What should we call light? Are radio waves light? And look into that. Think about what your answer would be. But we'll go on. We'll come back to the electromagnetic spectrum many times throughout the semester. So light is a wave, and we're going to start with a basics on waves. These little green tags here help you see which parts of Hecht to review after you watch the video, or before you watch, or while you're looking at the video. So the Hecht guide here says essentials about waves are on pages 10 to 12 and 14 to 16. All right, how do we describe periodic motion? Well, we usually draw a picture like this, and that kind of a wave thing, we might draw it versus time, or we might draw it versus position. This one's drawn versus position because we're also specifying the thing we call the wavelength. Right, so we've got a set of variables. The amplitude describes the maximum position from equilibrium, and its variable name is often A. The frequency, we're using nu, that's nu, nu, the Greek letter, is the rate of oscillation, and it's also related to the period, the inverse of the period. So to come to the period is the time for one oscillation, or one full cycle of a wave. And the wavelength, lambda, is the length of one oscillation. So there's some of our basic vocabulary, again, over here, just to give you a little bit of an idea of what units we use. Amplitude has units of distance. Frequency nu is units of hertz, 1 per second. Period, units of seconds. Wavelengths, units of distance. Let's jump right in. So in Hecht, you'll see a lot more information about the wave equation. I'm not going to emphasize that in this video. We'll emphasize how to use the wave equation, and in your homework and your work and your in-class work, you'll also look at how to use the wave equation. So here's a fact. Every electromagnetic wave satisfies the differential wave equation. What I've written here is the one-dimensional differential wave equation. It says that the partial derivative, the second partial derivative of your wave, your function psi, with respect to x squared, is with respect to x, is equal to 1 over v squared, your velocity v, times the second partial derivative of psi with respect to t squared. To get familiar with the psi, we're going to be using psi a lot. So any physical system that's described by this wave equation must involve traveling waves. That's interesting. That's what the wave equation means. Anything that's described by the wave equation has something to do with traveling waves. we will focus frequently for much of the semester on harmonic functions, harmonic waves, harmonic traveling waves. Lots of different ways of talking about this, but what we're discussing are sines and cosines. Sines and cosines can also be written as exponentials, which we'll get into in the next video. Any harmonic function, sines and cosines, satisfies the differential wave equation. So an example is something like this. A sinusoidal traveling wave can be written as a function of x plus or minus vt. Okay, psi of x and t is equal to f of a function of x plus or minus vt. So here's an example. A sinusoidal traveling wave would be something like a sine 2 pi over lambda times quantity x minus vt. Look, it's a function of x minus vt, and that is a sinusoidal traveling wave. We could also write this as psi of x and t is equal to a sine kx minus omega t. You'll see how these variables relate to each other in the next few slides. This 2 pi that you see in the a sine 2 pi over lambda is what makes this function repeat every wavelength. So notice that this 2 pi over lambda is pretty important. You'll also see something similar with time. Or 2 pi over t, 2 pi over the period, means that the function will repeat every period. And we call that a 2 pi periodic function. Right, so let's say we've got our sinusoidal traveling wave, something that we can write in various ways, and these are the questions that we're going to answer about it right now. We're going to say, what's its velocity? What are the units of k and omega? What is k and omega? And how are k, omega, nu, should be a nu here, and c, speed of light, related? All right, so let's start with what's its velocity. Well, this sinusoidal traveling wave, as written in either form, we have a sine kx minus omega t, and if we write it instead as a sine 2 pi over lambda x minus vt, these are the same thing, and this v is velocity. So the velocity is just v, and if we write it, if we could rewrite the first form the way I've got it here. If I pull out the k, I've got k times x minus omega over k times t. So what does that tell you? If you compare x minus omega over k times t, you see that that's the same thing as saying x minus vt, and therefore v must be omega over k. Okay, we just did something in a very rough way that I'm now going to describe by discussing phase. So I'm going to tell you a little bit about phase velocity, and I want you to notice where you should look for more detail on phase velocity in Hecht, pages 18 to 20. So phase velocity, what do we mean by phase velocity? Well, we just said the velocity is just v, where v equals omega over k. But what did we mean? What we meant was that velocity was the speed of the crest of the wave. In other words, you imagine this wave drawn right here, and at a later time, it would be in a different place. That wave, this particular crest, would be at a different location at another time. And we follow that crest to tell us what we refer to as just the speed of the wave, but what we really mean is the phase velocity. So what we've just defined is the phase velocity v as omega over k. And let's see on the next slide a little more math about why the phase velocity is equal to omega over k. Okay, we should start by talking about phase. You've heard of phase before when you first learned about waves, and then it got a little fuzzy. So phase, the phase of a wave that we write like this would be phi. Phase phi is kx minus omega t plus epsilon. Right. So what we look for is the argument of the sine function, or the argument of the cosine function, or the argument of an exponent. That's the phase. In other words, it says, where are you in your peak or trough? Where are you in the cycle of the wave at some particular time or position? It tells you the phase of the wave. Epsilon we're going to write as the initial phase so that we don't confuse initial phase with total phase phi. Okay, so if that's the phase, then the phase velocity is when the phase is the velocity given that the phase stays constant. In other words, the position with respect to time at constant phase. Position with respect to time at constant phase. There's a math theorem that tells you that the partial of x with respect to t with constant phase is equal to minus partial of psi with respect to t, partial of phi with respect to t with constant x, divided by partial of phi with respect to x at constant t. So this is a mathematical given, and it's known as the condition at constant phase. Let's take our partial derivatives. Partial of phi with respect to t is minus omega. Boom, minus omega. There was an extra minus sign, so that's why we just got an omega on top. Partial of phi with respect to x is k. So we throw our k in down here, and look, we've got that the condition of constant phase is omega over k. That's what we said before, that v equals omega over k. All right, so we're going to move along here. We'll look at more of the variables that have to do with waves. There's our sinusoidal traveling wave. And let's remember that lambda is the wavelength, units of length. Okay, let's figure out what k is first. Look at the two expressions above. We've got sine kx minus omega t here, and then we have sine 2 pi over lambda times x minus vt. That tells us that this variable we're calling k must be equal to 2 pi over lambda. This k is one of the most important variables you'll use throughout the semester. This variable k is called the wave number, or wave vector if it's in vector form. And you can see that it must have units of 1 over length, because lambda is units of length, must have dimensions of 1 over length, and the units we'll use are 1 over meters, or inverse meters. All right, for the units of k. Let's move on to find the units of omega. So omega is the angular frequency. Let's compare this omega with what's going on over here. You'll see that omega is going to be equal to 2 pi times nu. This is a little confusing. Okay, because this is a nu and that's a v, and that's going to be our biggest issue with using nu as a variable. So notice it now. This is omega equals 2 pi nu, and the angular frequency is related to the frequency nu as omega equals 2 pi nu with units of radians per second, or what we write as inverse seconds. When you multiply out your 2 pi over lambda times v, and then put in your k as well, you'll end up with, make that as an exercise for the reader. Try writing that out. We can do it in class as well. You'll see that this works out. Okay, so now let's focus on how we relate all these variables. We've just looked at lambda and k related. We looked at omega and nu related, but now let's think about c. The speed of a wave in vacuum is c, and so that was pretty straightforward. C is omega over k because it's just the speed, v, and given the previous variables we've had, c equals lambda times nu. All right, I have an opportunity to use my very favorite mnemonic, which is, what's new? C over lambda. That is how I remember the order of c equals lambda nu. In other words, what's new? That's on the left-hand side. C over lambda is on the right-hand side. I'll say it because I can't help it. And I encourage you to just, if you need mnemonics, this is one of the most frequent expressions we'll be using. So it's a good mnemonic to have. Okay, that was a lot of definitions. A lot of definitions. All these are in the text, and we'll start working with them in class. Now, every electromagnetic wave satisfies the differential wave equation. We got there already. What is that going to mean? We remember that that means that our physical systems described by the wave equation involve traveling waves. So let's try it out. Let's figure out if some particular function is a wave. There's two ways of doing it. One is to substitute the function into the wave equation. The other is to express the function psi of x and t in the form f of x plus or minus vt. F here just means it's a function of x plus or minus vt. We're going to try each one of those. Let's first do something else with waves, and let's show that this function of x minus vt, is a forward traveling wave. Okay, here we go. Suppose that that x minus vt is constant. In other words, the whole quantity x minus vt is constant phase. If we take a little change in x and a little change in t, then we'd have dx minus v dt is 0, because if x minus vt is constant, then a little change dx minus a little change in time is going to give us 0, because the derivative of a constant is 0. All right, now solve that for v. We get v equals dx divided by dt with a positive sign, which tells us that the velocity must have been in the forward traveling direction. The velocity must have been positive. If that sounds confusing, go through that whole thing again. Try it out, switch the sign, see that you get a negative traveling wave. So the function, any function of x minus vt is a forward traveling wave, and similarly, any function x plus vt is a negative traveling wave, or a backward traveling wave. Right, let's do an example where we take this function x plus 3t squared and show that it satisfies the wave equation. Let's use method 2, because it's pretty easy. This function is already written as a function of x plus vt. Right? It's a function x plus vt, and the velocity is negative 3. Okay. Why did I just do that? Because the velocity is in the negative direction. We know, because it's a function x plus 3t, that the velocity, it must be traveling in the negative direction. So if we include a direction with our velocity, the direction is negative. Look at this MATLAB representation of this function at two different times. At time t equals 0, we have the blue line. T equals 1, we have the red line. Notice it's moving to the left, and that is a traveling wave. It's not much of a wave. This is the, it doesn't look sinusoidal, which is what we're used to, but it's a traveling wave because it has a profile that is moving to the left, and it's a function of x plus vt. Let's do this with the other method. This is really heavy-handed, and I write out this so that you can see what partial derivatives look like. When we do the partial derivatives, we take the first derivative, and then we're still left with another derivative. So you take one derivative with respect to x, you get 2 times x plus 3t. Take the second derivative with respect to x, you get 2. Now let's do the derivatives with respect to time. Take the first derivative with respect to time, we get 2 times 3 times x plus 3t. Take the second derivative, we get 2 times 9. Why did I write it like that? You'll see in a moment. Substitute that into the wave equation. So you've got your partial derivatives with respect to x on the left. That was 2. Then you have 1 over v squared times partial derivatives with respect to y on the right. And these are equal to 2 times 9. Let's solve now for v. And we see that v squared equals 9, or v equals plus or minus 3. Good, because in our previous technique, we decided that the velocity was equal to minus 3, and the speed is equal to 3. Okay, so we just did two methods with something that looks like a straightforward function, but the derivative took a little time. Okay, so what we've just done is we've seen how we can describe waves using a variety of variables, and we've looked at how to show that some function of x minus vt, or kx minus omega t, is a wave. how to find the velocity of this wave using the two different techniques, and how to determine the direction of the wave. We'll do more work on this in class and in homework.